Okay, let's take a look at a very important aspect of magnetic fields, and that is, what is the force that in a magnetic field would apply to a charge moving through that field? All right? And the first thing we have to do to begin looking at this problem is have a notation for what magnetic fields look like on the page. Okay? And so here's this notation. If you see these little X's like this, that means there's a magnetic field going into the page. Okay? Almost like if you were to like shoot an arrow and you see the fins moving away from you, that means the magnetic field is moving away from you. Right? And if you have a magnetic field coming out of the page, right? So here's your page, magnetic field's coming up, then you have these little dots, almost like the arrows are coming at you. Okay? So out of the page, into the page. All right? And so we want to take a look at, let's say that we have a little proton, okay? And we shoot it into the magnetic field. Okay, so now we have this electron or this proton over here moving through this magnetic field, pointing in this direction. Okay, it is going to feel a force. Right, when there is a particle moving perpendicular to magnetic field lines, there is always going to be a force. All right. Notice I said perpendicular. If the charge is moving parallel to the magnetic field lines, there will not be a force, and we're going to explain why that is in a second. Okay, so in order to find out what direction the force is going to be acting on this particle, we need a second right-hand rule. All right, so the first right-hand rule gave you the direction of a magnetic field as a result of a current. Okay, this right-hand rule is going to be the direction of a force experienced by a charge that is moving through a magnetic field. Okay, so the first right-hand rule gives you a magnetic field. The second right-hand rule gives you a force experienced by a charge moving in a magnetic field. Okay, important distinction. So we have two different kinds. All right, this second right-hand rule says this. Okay, and it's explained more on the next slide. But the first thing you have to do is you have to rub your hands. I'm just joking. It's not part of it. It's not. Okay, but you have to take your hands and you point your fingers in the direction of the moving charge. Okay, the charge is moving that way. Okay, this is almost like physics and yoga combined. I feel like I'm doing warrior pose or something. I don't know. Anyways, it's been a while since I took a yoga class because of COVID. Anyways, so the particle's moving this way. The second thing I do is I point my palm in the direction of the magnetic field. So in this case, the magnetic field's going this way. So I point my palm, and you guys should be following along. I point my palm in the direction of the magnetic field, which is that way. All right, and then my thumb then is going to be the direction of the force of the particle. Okay, so again, fingers point in the direction of the motion, of the velocity. The palm points in the direction of the magnetic field. Sometimes I like to curl my fingers in the direction of that magnetic field. That's fine too. But the thumb is the key. The thumb is the direction of the force. That means this particle would feel a force up, and it would begin to swipe up like this. All right? Pretty basic, okay? Let's try another example. Let's say that we have a proton moving in this magnetic field, okay? We do the same thing. Take my fingers, point it in the direction of velocity. Velocity is that way, right? And now I'm going to point my palm in the direction of the magnetic field. That is out of the page, right? Out of the board this time. So I curl my fingers towards that B field, and my thumb is what's left. That means that this particle would feel a force. If it was moving this way, it would feel a force in this direction, down, right? So it would kind of swoop down like this, okay? And we are going to talk more about what that path will look like once it continues that motion. But for right now, just know if you follow the right-hand rule, a proton moving in this magnetic field will feel force up, and a proton moving in this magnetic field will feel force down. Okay, what if we switch it? What if we make these electrons? Okay, so I'm going to erase the little plus here. I'm going to make them minuses. Okay, and now I'm just going to go ahead and take away all the forces. So the only difference is basically everything that happens to electrons is the opposite of what happens to protons. So there's two things you could do. You could still do the right-hand rule and just say the force is the opposite direction, or you can use a left-hand rule, right? So I'll show you both really quick. So if an electron moves through here, right, I still use the right-hand rule. I say my finger points in the direction of the particle, right? My palm points in the direction of the magnetic field, and then there's going to be a force pointing upwards on this charge, all right? So, but I say it's not positive, it's an electron, so that means the force is actually down. So an electron moving through a magnetic field going into the page would have a force going down and would swoop down like this, okay? And the same thing would happen here, except it would be the opposite, right? Again, my hand pointing in the direction of the velocity. I put my palm in the direction of the magnetic field. It says the force should go down, but I'm like, no, it's an electron, so actually the force is up and it will swoop up, okay? The other thing you could do is just a left-hand rule. So if we do that for the top, right, I say fingers point in the direction of the charge, all right? The magnetic field is into the page, okay, which means my thumb points downwards, okay? And is that the direction of the force? Yes. So that would be the particle swooping down. All right. Now, there are many videos on YouTube about the right-hand rule, especially as it pertains to magnetism. So if this little rundown was insufficient and you want to get some more practice, you can just Google right-hand rule magnetic force on the YouTubes, and they will give you all the different options, all the fun options for how to look at this, many other examples to practice. But that's just the way it is. You take, if you have a proton, you point your fingers in the direction of the velocity, point your palm in the direction of the magnetic field, and your thumb then is the direction of the force on the particle. Okay? That just leaves one question. What is the magnitude of that force? How big is it? How do we calculate it, right? And the answer is actually quite simple. The answer is that the force on these charges, so the right-hand rule gave you the direction, but if you want the magnitude, if you want to be able to actually calculate the force, then that's going to be QV cross B. And some of you may remember from last semester or from calculus, or when you learned how to do cross products, right? You may have learned that a cross product is really just the magnitude of everything times sine theta. And as far as this course goes, this is all you really need. So the force acting on a particle moving through a magnetic field is given by the charge of the particle times the particle's velocity, right? So this is charge times velocity times the magnitude of the B field that it's moving through, right? And these all have to be SI units, obviously, so coulombs, meters per second, and Tesla, okay? And this theta, this angle is between the velocity and the direction of the B field, right? So what is the angle between the velocity and the B field? Well, in these cases, it's very, very easy, right? I'm going this way, the B field's going this way. That's totally perpendicular, right? So that would be just sine of 90. So if they're totally perpendicular, sine of 90 is just 1. So in the event that the charge is moving perpendicular to the B field, the equation is a little bit more simple, right? But if we have a situation like this, where we have a B field, let's say pointing upwards, right? And there is a charge, a proton, let's say, that's moving in this direction, right? Then there's this angle between them, and so that angle goes into sine theta here, okay? In the next video, we're going to actually get some practice in using this equation to solve for the magnitude of various forces. I'll see you there.